Hi, today we are going to go through a proof of the Black Scholes formula. There are actually different ways to prove the Black Scholes formula, and today I'm going to go through a more intuitive method, and maybe in a future lecture I can go through using the PDE approach. Okay, before we go into the proof proper, I think we should walk through several mathematical formulas so that those who are unfamiliar can follow through. Alright, the first one is the concept of expected return, or rather expected value. Maybe let's start from a sort of a discrete example. Let's say we have a game whereby there's two outcomes, A and outcome B, and the probability of A happening is, say, probability of A, okay, probability of B happening is probability of B, and these are the only two outcomes, so the two probabilities will add up to 1. Okay, so what is the expected value of this game we call X? Okay, this is simple. It will be outcome A multiplied by probability of A plus outcome B multiplied by probability of B. Okay, so this is what is known as expected outcome of X for discrete function. But how about a continuous function? For a continuous function, it's no longer a probability A or probability X, because we cannot express because it's continuous, we cannot express the probability to each of the variable. So collectively we call the probability density function of a continuous variable as, say, probability X. So this is no longer a single number, this is a function. Okay, so we can express this function as follows. Okay, so assume that this is, this function is like that. So for every point X, there's a probability associated with it, and the area below this function adds up to 1, because we need to force the probability to be equal to 1, and that's the nature of probability. Okay, so what's the expected value of X in this case? It's no longer like that, but the concept is very similar. It will be integral from infinity to minus infinity. Okay, basically we're going to cover the full range of X. It will be X px. Okay, it's very similar. In the discrete example, we have X multiplied by probability. So it's for the continuous example, instead of adding up, we have an integral function which is very similar to addition. Okay, and a dx here. So it's basically X here multiplied by the probability and then integrate it. So that's the expected value of X for a continuous example. Alright, another concept that we want to go through is the concept of normal versus a log normal. This is one key assumption of Black Scholes, is that stock prices is denoted by S follows a log normal distribution. Okay, or rather, to be exact, we have to say that log S follows the normal distribution. Okay, which actually means that the stock prices S follows the log normal distribution. This is an assumption of Black Scholes. Okay, for normal distribution, we can denote it in this notation, and we can call the mean M and the standard deviation sigma for the log S distribution, because it's a normal distribution. The expected value of S can be expressed as a function of M and sigma using one of the properties of the log normal distribution. Okay, so expected value of S is equal to M plus sigma square over 2. Okay, next I want to show you how the normal graph looks like. Okay, so log S will look, this is how a probability density function of log S looks like. It will look like this, because it's a normal graph. it's a normal distribution whereby this is M, and the area under this probability density function is 1 because it measures the probability of log S. Okay, so let's say log S is here. This is the probability that this value will occur, and so on and so forth. And the log normal graph looks like that. Okay, looks different from the normal function. It's certainly not symmetrical, and it doesn't go into the x-axis, which is a good property to have for stock prices, because stock prices doesn't go negative. Okay, I can also illustrate the concept of a cumulative distribution function of a normal distribution. So let's look at this normal function and assume that we are at this point x. We want to know what is the probability of x smaller than, we want to know what's the probability of log S smaller than x. Okay, so this is represented by area here. Okay, so assume that we draw a graph to denote this probability. So the y-axis will be probability of log S less than x, and we have x here. Okay, so this probably let's say it's here, maybe 0.1. okay, and so on and so forth. We can plot x1 here. So x is here, so we have this point, and then we have x1 here, and let's say, let me use another color. Okay, probability of log S less than x1 will be a larger number because the area is larger. So let's say it's here. Okay, let's say it's here, and so on. And we can see for ourselves that at M, half of the graph is on the left hand side, half of the graph is on the right hand side, which means that at M itself, right, the probability is 0.5. okay, because we know that the whole of the area is 1, so as at M is 0.5. And how about the right hand side? We know that the whole area is 1, so if we have 1 here, we know that the graph, the cumulative distribution graph, never cuts 1. Okay, so all in all, if we continue our whole argument with the right hand side, the graph will look like that. Cuts x-axis, cuts y-axis at 0.5, and we'll look at that. Okay, so this is what we call a cumulative distribution function. Okay, it's useful because whenever we want to know what is the probability of, say, log S less than a value, you can simply look up this graph and then just look up what the y-axis corresponding to the value here. Okay, another property that I want to show you with regards to the probability density function is how we can normalize a probability density function, meaning that we have log S here, how we can express this into another function such that it becomes a normal with mean 0 and standard deviation 1. Okay, so let's call this function Q. How we can transform log S into Q such that if Q is a normal function with mean 0 and standard deviation 1. question is, why do we want to do that? The reason is because when a normal distribution with mean 0, standard deviation 1, the probability density function has a closed form solution, which can be expressed as let's say the probability density function of f x is equal to 1 over root 2 pi exponential minus x squared over 2. Okay, so this one is the probability density function of a standard normal distribution. It's more straightforward than a non-standard normal distribution. So how can we do that? We can simply express Q as log S minus M over sigma. Okay, so once we do that, the original log S normal distribution function will become a standard normal distribution function Q with mean 0 and standard deviation 1. Okay, now we are ready to go into the proof of Black Scholes proper. Let's move on to option pricing. We assume that there's an option that we need to price, a European call option. It's an equity option, and the strike at K, and we want to price it by taking the expected value of the payoff at the end of maturity and then discount it back to the present value. So clearly there's a discounting element here, and here's the expectation of whatever that we have at payoff at the maturity point. What do we get at the payoff at the maturity point is the strike, the spot at the maturity minus the strike. Okay, if it's less than 0, then we take 0. If it's more than 0, then we take this value. So there's a max here. And we also assume that the PDF of the spot price movement S is given by this function GS. Okay, and we have shown earlier that expectation of a continuous function is basically the integral of the PDF multiplied by the variable itself. In this case, K is a constant, so it doesn't really matter if we put K here. Okay, and we integrate here, and notice that we are integrating from infinity to K instead of infinity to minus infinity, as we have shown earlier. Okay, so if I draw the log normal graph, it's basically we are trying to integrate K to infinity here. Okay, so we are doing this. We don't want to integrate throughout the whole curve because the payoff only happens from K to infinity, only when spot moves beyond K. So it's integrate from K to infinity. Okay, so this is S is log normal, and this is the assumption that Black Scholes made. So log S is a normal PDF with mean M and standard deviation sigma. Okay, so expectation of the log normal S is given by this function, as we have shown earlier as well, and hence by rewriting this function, M is equal to log expectation of S minus sigma squared over 2. Okay, basically the whole point of this proof, right, is we are trying to create a normal function out of this log normal function. Okay, so if we look at this, log S is a normal with mean, mu, and sigma. We try to standardize log S by subtracting the mean and dividing by the standard deviation. Okay, so we define a new function Q, where Q is log S minus M over sigma, and Q is a standardized normal distribution with mean 0 and standard deviation 1. Okay, because log S is a normal distribution with mean M and standard deviation sigma, so we standardize it we get the standard normal distribution. And the PDF of Q is very simple. It's this expression. It's a known formula. Okay, so with this, let's look at this, the call price function again. Okay, we want to rewrite this function so that this function is expressed in terms of Q, which is the standard normal distribution. So S now becomes this one. Okay, you just from here you just express S in terms of Q. So S becomes this one. So now the PDF of S now becomes PDF of Q. Okay, integrate with respect to Q. And also one more thing to note is, instead of K here, we are writing log K minus M over sigma. Okay, because instead of S, we have to instead of S, we have to change it to be expressed in terms of Q. Okay, so Q is written as log S minus M over sigma. So we should write log K minus M over sigma here. So now the integration is from here, log K minus M over sigma onwards. Okay, so it's this area, and now it has become a normal distribution. Okay, okay, so I've expanded this by splitting up the K term and the exponential term. Okay, so there are now two terms here. Okay, if you look at this function h, the PDF can be expanded by putting the h. Okay, h. Let's put h inside here, and it can be expanded as follows. We want to write. Okay, yeah, it's a simple expression, so I'm not going to explain it further. Okay, so essentially what we want to do is we want to obtain the exponential function. We want to obtain it in two different expression. Okay, why do we want to do that? Because if you look at this entire term, okay, it looks really like the h term here. Okay, except that the Q here is now in terms of Q minus sigma. So basically this is a function PDF of Q minus sigma. Okay, because of here. And then this is this one. Okay, so now we can write this one in a more compact manner. Now we can bring this one out of the equation, because integral has nothing to do with here. There's no Q term here, and this term remains inside the integral. And if you look at this term, this is a normal function. So basically we are integrating a normal function. Okay, so this is actually the area under the curve. So the area under the curve, and but the question is, what is this? What is this? Right, and it's given by, it should be this one, right? But note that there's a minus sigma here, so it should be this value minus sigma. So it's log K minus M over sigma minus sigma. Okay, so this value is given by log K minus M over sigma minus sigma. So our objective is to find this area. Okay, but notice that this is a normal function, so actually there's a symmetry of the normal function. So actually, when the curve is symmetrical, if you find the area under the curve from minus of this expression here, log k minus m over sigma minus sigma. Okay, negative of this expression here, and you find the area on the curve from minus infinity to this point is the same as finding area under the curve of this expression here to infinity. Okay, so the area of minus infinity to this point is actually the CDF function. If you recall, the CDF function looks like that. Okay, this is 1, this is 0.5. Okay, so we just bring it down, and then this is the value that we want here, and this is written in again a compact form by this notation n. Okay, n represent the CDF of the function inside, and simply rearrange the formulas inside, and you will obtain the common expression for Black Scholes, which is ND1 here. Similarly for this one, and it's even simpler here because there's no minus sigma term inside. So you have something like there's no this term won't be here for this expression, and then you obtain ND2 here. Okay, this one will become ND2, and after this, simply rewrite the expressions ND1, ND2 into here. Okay, remember the discounting function here, and then for this one, right, this is basically here, this one, and m is what we have discussed previously. M is simply the log expected value of s minus sigma square over 2. So we can cancel these two terms, and expected value of s comes out with, and then multiplied by ND1 minus k multiplied by ND2. Okay, so if you recall, we can, in a risk neutral world, we can write expected value of s in terms of s naught multiplied by e to the power of RT. Okay, put this in, and then lastly we need to rewrite the sigma in terms of let's say sigma, because sigma is always a variable of time. Okay, so, or rather it's a variable of root time. So if you write in a more specific and exact manner, it should be written as sigma root t. Okay, if you rewrite this one, and this one into this expression, you'll get the Black Scholes proof. Alright, that's all. Thanks.